Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 1 of Arrow 4080 Finite Elements. Today we're going to be starting our journey into finite elements, how we can idealize structures in each of its little components and get meaningful and quite powerful solutions to structural problems. So first we're going to kind of do a preview of what finite elements actually is. So our general concepts. Okay, so this term finite elements, now this isn't really going to help you be a better finite element analyst, but understanding some of this background can help to set your mind for where we're headed. So the idea of finite elements, so you've already done structural analysis. We've analyzed little rods in tension or compression. We've analyzed bending and shear and these different things. Most who have done it for fairly simple structures. Sometimes we do it like with trusses where the entire member is under the same loading. Other times we have multiple intermediate loads on a beam, for instance, where we have different loads throughout the member. Now, if we're dealing with just a single structural element, a lot of times we can do that analysis by hand. But when we have complex structures consisting of many members, the analysis can get quite detailed, and the number of unknowns make the problem indeterminate, which becomes unsolvable. Now, we learned some indeterminate methods all the way back in statics, and then more so in 3261 in our Structures 1 class. For example, our thermal problems, where if it was restrained in a poor manner, then we had too many constraints to solve the problem, but then by statics alone. But then what we found was by accounting for our displacements, we could solve the structure. And we saw other examples of that where whenever we had too many unknowns to solve using statics alone, we would try and account for the displacements, and usually the math got complicated rather quickly. Not that the math was so difficult, but solving some of the simultaneous equations was. Finite elements handles all that for us. Basically what we're going to do is break our structure into a series of elements. There's a considerable amount of judgment in figuring out what structural elements we can idealize. You can take an aircraft and idealize it with just a few elements if you want a very coarse model, just to understand how the thing flies through the air. In fact, you can idealize it as just a point, like a dot, as we did back in dynamics, before analyzing it as a rigid body. We can then go to a more complicated model where we idealize our stringers and our frames and different pieces, and we can get more and more fine models which become larger and larger mathematical problems. So the idea of the finite element, the term was coined in the 60s, and there are various books on the subject. This became popular by the end of the 60s to early 70s. Finite elements was becoming a key way to analyze large indeterminate structures like aircrafts and other flight vehicles. Now back then the computers weren't very strong. They'd have a computer in a room that was weaker than the little hand calculator that you have today. And because computing has advanced so much faster than some of the background technology behind the methods, more detailed models are used today than were able to be used before. So there are a bunch of finite element model software packages. SolidWorks has its own. A lot of the CAD software for drawing structures have their own. A lot of times that software is inferior. It may be really easy to use, but it's inferior to the ones that have led the charge, like the NASTRANs, some of them specialty ones like the Abacuses, and some others. So basically we're going to be using what's called the finite element method. So these are a couple acronyms. We're going to look at this in a bit. Finite element FEM, F-E-M, stands for finite element model, which can also stand for finite element method. FEA stands for finite element analysis. These words can be used nearly interchangeably. Or you might just see FE, meaning finite element. So basically what we're going to do is take a structure, we're going to break it up into elements. We're going to say, okay, I'm going to idealize it in this element, this element, this element. We're going to have to tell the machine, the code, the software, what stiffness this has. Is this just an axial member that can carry axial load, or can it carry shear, can it carry bending, those kind of things. All these decisions have to be made. Just drawing a model and letting the computer do its thing is not sufficient for many models. Okay, we're going to have points. So in order to do this, first we're going to have to make a judgment call about what kind of elements we're going to use. And then what we're going to do is have to figure out where these elements are and how they connect together. Now, where they are is less important than how they connect together. But where they are determines what the boundaries of each element are, and then the program can figure out connectivity from just the locations and the way that your model ties them together. So we're going to be using things like nodes. We're going to be identifying points in the model. We call these either nodes if you're using Abacus or Strudel, or grids if you're using NASTRAN. We're going to develop elements like rod elements and bar elements. Rod elements have axial capability. Bar elements have shear and moment capability. Plate elements, you can deal with flat plate elements like a quad element, a C-quad element in NASTRAN, which would have 4 corners and have in-plane stiffness and other higher elements. We're going to look at some of these. We're going to keep it simple because a lot of times you can use some of the simplest elements to do some rather complicated modeling, and if you keep your elements simple, it keeps the output understandable, so you can then, after you're done, do something useful with the model rather than just look at a bunch of pictures which are completely meaningless. So since we're breaking our structure up into elements, there is a finite number of elements, hence the word finite and finite element. Okay? So basically what we're going to be doing is, now there are a number of methods which use functions and things to define how these pieces interact or connect. But basically we could go back to our old spring idealization that we learned back in physics. We knew that the force in a spring is just the spring constant K times the displacement X. And that's basically true across the board. Now, if you have an axial spring, that's pretty straightforward. If you have a rod, it's going to work the same way. If you know what the stiffness is, you can just multiply by the displacement. That will give you the force, or solve that in another manner. If you have a plate, you're going to have stiffness in the extensional direction and the shear direction and in the rotational directions, maybe in 3 directions on each one. Okay? So basically the idea behind this finite element method is most or many finite element methods, all it involves is idealizing your structure so the computer software can figure out what elements you're using and how they're tied together. Your software is then going to create a stiffness matrix. It's going to represent the stiffness of each structural element and then put it in a huge matrix that places all of the stiffnesses in relation to the other so we can see all the interactions between the different elements. Elements that are going to connect together. If you have multiple elements attached to a single point in your model, then each of those elements may contribute to the stiffness at that point. And the stiffness at that point is really a function of the stiffness of each element that's attached. So that's basically what it's going to do. Once this software creates this large stiffness matrix, which means it's figured out a stiffness matrix for each and every element, and then it's assembled those stiffness matrices into a large matrix, then it's going to look at the applied loads and constraints and then solve that system of equations using fancy numerical methods that you will learn a little bit about when you take your numerical methods class. So basically we're going to have an equation, Kx equals F, and the inverse of that equation. And we can do this most commonly for like forces and displacements, which gives us stresses and strains. We can also do thermal analysis with this. We can do velocity analysis if we get into a more complicated code, and other kinds of analysis. Okay? We're going to try and keep it simple and keep it usable in what we cover in this class. So what it can do is basically the beauty of a finite model is it can take a complicated structure that's indeterminate and make it rather simple. Instead of having to solve this huge math problem, all you're going to have to do is solve an idealization problem and to clearly communicate with the computer about what kinds of elements you have, what stiffnesses they have, how they're attached together, how they're loaded, and how they're constrained. Those are the major building blocks. And then the computer will take your model and it will run that in the code which will generate output. And then you have to read the output and understand how that works and what that means. All right, so because we are idealizing our structure with little elemental pieces, which means we've taken and broken up into a bunch of pieces and ignored a bunch of other things, all the solutions we get out of this are going to be pretty approximate. Sometimes they'll be pretty close to being correct, other times they'll be pretty far from being correct. And so Finite Elements is going to give us an approximation of reality that can be fairly accurate. When they talk about exact solutions, they're usually talking about a solution of a problem that could be solved by hand with an exact method that should be exact within the consumptions in that basic analysis. So basically what we're going to do, when we talk about pre-processing, what we're going to do first is build a model, which means we've got to look at our structure and figure out what elements are we going to use, how is it loaded, how are these elements tied together, what kind of constraints do we have. This is the process of building a finite element model. And we can either do that by hand, we can actually make a text file. You're going to learn how to do that. We'll make a text file that has all of the information we need that the computer then reads and then constructs into a mathematical problem. That's called pre-processing. Or you can use a pre or post processor. All that SolidWorks does, and Patran and FEA is it creates a graphical interface that's like you're drawing the part, and then it's creating that little model for you. Okay, so we're going to pre-process that, then the computer or the software is actually going to evaluate that model we create, and then post-process is the idea of once we've done running, either we're looking at output or we're looking at a pretty screen which has information coming back from the output that allows us to analyze what just happened in our model. Did our model run? Did it have a fatal error? Did it run successfully? What kind of results did we get? Did we get the results that we need? Do we even understand the results and what do those mean, and how do we turn those into stresses, and how do we write margins of safety? Okay, that's the post-processing step. So that was a kind of a brief overview. Going back to our nomenclature, FEM stands for Final Method or Final Model. These are used nearly interchangeably. FEA usually means Final Element Analysis. The abbreviation FE often means Finite Elements. We mentioned this earlier. The word model is kind of our idealization. It's what we're pretending, right? It's kind of like a avatar, right? It's like an avatar or a cartoon, an animation of what's reality. An avatar is just like a drawing, a sketch, or an animation is a drawing of something that's actually not exactly what it is, but it appears like it and it looks like it's good. That's what these models are. We've been using modeling and idealization from the first days of our structural journey, and this just takes that a step further. Idealization is similar because we're idealizing or pretending that our structure behaves in certain ways and that our constraints behave in certain ways. Okay, we're going to be learning how to make these kind of assumptions, how to make gross judgment calls, and idealize our structure in these ways. This is another little slide that's intended to show you a step-by-step procedure where we're going to select an analysis type. We're going to start off this class mostly looking at linear structural static analysis. Linear meaning our problems, we're going to pretend that they remain in a linear range. There's no nonlinear behavior like due to material geometry or due to materials or geometry. Later on we'll learn some other things, like we'll learn to do a little bit of thermal analysis and some other kinds of things. Okay, we're then going to go and idealize our structures and select what kind of elements we might need. We're going to choose material properties for each and every element that we have, and then we're going to go create nodes everywhere where we need an interface, and then idealize our structure with elements tying them from node to node. Then we'll apply boundary conditions and loading. We'll run that model and we'll try and understand it. That's the basic process. Okay. This is kind of a slide. This is just a pin-to-pin beam with a pressure load, and this is a dynamic load, shows the displacement as a function of time. As you can see, this can be very difficult, and you can see all these different codes are giving completely different responses. That ought to scare you a little bit. Just because we run a finite element model doesn't mean it's going to match what anybody else says or what any other code says. And what that should tell you, if you see this kind of disparity in the results that we're seeing, is that there's probably some error associated with a finite element analysis, especially for complicated methods like this one. Okay. All right, so just to look at a couple examples to kind of get your inspired to do great work. This is a fairing off of a delta 3. The fairing obviously is pointed up toward the sky. This is laid on its side here. And this is a dynamic analysis, so we're actually doing, we have a kind of a fine model. Basically, this is a composite sandwich shell. And when we applied our loading, our dynamic loading, or actually this is just looking at the structure itself and the stiffness of the structure and how it buckles as a function of that stiffness under pressure. This is a pressure buckling, so similar to what we learned in 3271, where we looked at buckling of cylinders and things under pressure. This would be a buckling of a cone. You can see when we apply a pressure here, we find we get an eigenvalue of 1.337. We have a factor of safety buried in our baseline analysis, and we can use that to write a margin of safety. Okay. Now the displacements here are greatly exaggerated. Whenever you look at displacements, whether it's a dynamic model or a static model, usually it'll look like the structure is kind of moving all over the place. That's because they show the displacements usually with a factor of 100 or even 1,000 times the actual displacement. Otherwise, you wouldn't see it. They wouldn't look like it's doing anything. So this allows us to see with our naked eye how the structure is responding. We can gain insight about the problem from that. This is another model, a dynamic model, looking at the stability of the inner stage of a delta 4 for compression. This finds that we get a little peaking near the door, and that drives a stability problem right off the door corner where the stresses are maximum. This one is a detailed axisymmetric model, which means instead of modeling the entire lux skirt structure that's below on part of the cylinder of the Delta IV rocket, we're looking at a tiny piece, looking at the core, the sandwich material where it goes to a closeout, and we were worried about the temperature and stress effects right there in the soft core. This is a detailed model. So an axisymmetric model is one where instead of modeling the whole structure, if you need all this detail, you can just model one little strip through the thickness and then tell the computer information about the symmetry of the thing, and then it puts in boundary conditions that will allow you just to look at a single cross section and see how the stresses are. And this is some stuff. The larger picture here, you can see the pressure dome of the tank with the lock skirt just above it and the cylinder of the tank just below it. And we see a little detail of where this little detail model, this axisymmetric model, is. The model on the left is the static model using Abacus and Patran, looking at the stresses in the core, and the model to the right is, I think that's using Cinda, was generated by the thermal analysis group with temperatures. Here is a thermal shield on a Delta IV structure, a typical finite model, and the kinds of, this is showing just the different elements, sizes that we use for doing some analysis. Here's a payload attach fitting. This was for a Delta III, and we were looking at a discrepancy where they had a little crack that was found during the ultrasound. And this is the model showing the meridional and hoop stresses. We looked at the baseline model without the defect, and then we modeled that defect in a slightly more complicated model, looked at the meridional loads, showed that they weren't a whole lot different, and that our structure was fine in that respect. Here's a detail up at the forward attachment of the payload attach fitting. This was because we found a little bump. You can see cross section with a micrograph over here to the far right, and you can see how there was a little bump. They made a little glitch when they were creating their composite sandwich. They didn't get the bagging and everything situated properly with all the plates and things to hold geometry, and they got a little bump there, and they were concerned about a local stiffness problem. So we created a little finite model to simulate that, and then analyzed it and showed that we were acceptable for the loading that we had. I was using Abacus. Here's a little detailed model of the separation system. When you have the inner stage, remember, all the inner stage on a rocket will fall away after you're done with the second stage. Right before you use the second stage engine, when you're done with the first stage engine, it drops the first stage away. This was the sure sep of the, this looks like I think this was the Delta IV model, and this was a detailed model where we have it kind of designed to fail right there, and we were studying stresses in the critical region. It's a very fine model. We're not going to get into that detail in our class. This is a nose model for an MD-11 that I created back in the early 90s, and this is showing, this is mostly a semi-monocoque structure. The stringers start just behind this door, so this is mainly just intercostals and skin. It's all pressure critical, and this was a model that I used. This was first created in CASD and CGSA, and then was converted to NASTRAN, CGSA, and eventually to NASTRAN, PATRAN for analyzing this structure. This is a little different kind of model. This is called program Crash. This is a program developed by NASA for the FEA, and basically what this is for is doing large displacement analysis of structure, especially for crashes. So this is a cross section of a single typical frame spacing of like the frame stiffness of like 1 bay between one passenger to the next. You can see the floor and the struts and a rough model of the frames, and then you can see the seats are modeled, and then the little people are modeled. There is a single rod, so we could extract the dynamic G's at the neck and back of a passenger, as well as the spinal force, which is critical. And we're doing this because in the early 90s we were going to place passengers down in a lower cargo compartment, create a passenger compartment so they could look at these windows looking down, and to keep them from being, to try and give them the same level of safety as we have for the passengers on the upper deck, which is basically impossible to try and give them a similar level of safety. We put a bunch of energy absorbing honeycomb down on the bottom of the structure, and we're evaluating the spinal loads and making sure that our design would be good. We never actually built this plane. I did a lot of analysis using first-hand analysis, and then NASTRAN linear analysis, which doesn't even apply, but kind of trying to get closer and closer to a better solution. Then I tried to do a nonlinear solution with die-cast, and then I ran this crash program, which was developed just for this purpose, used especially for helicopters and things. We applied it to this structure, and then when once I sold it to upper management that we were going to go and build this, that we could build this aircraft, we were going to take a cross section out of a fuselage, put dummies in there, instrument them up, and actually drop the structure. And we were about a month or so away from running that test when that program was canceled, unfortunately. Super fun stuff. So we see that Finite Elements is a powerful tool, and we have to be careful when we're making our final models. So a lot of folks today tend to think, hey, you know, if you don't understand what the structure is doing, don't do a hand analysis, go and run a final model. Well, that's because they don't know much about hand analysis, and they don't know much about final models. Hand analysis, we make gross approximations. You've been learning that through the structures journey. With Finite Elements, we make even more gross assumptions, and those assumptions are hidden from view, hidden from the users, and all they see is like a pretty color plot, and it's very difficult to find out what all those assumptions are, where the problems might be. So Finite Elements are a tool to do a lot of good or a lot of damage, but we have to be careful with how we apply them. Okay? We should always try and come up with a hand analysis to idealize our structure as well as our final analysis, especially as we're developing the judgment of understanding how these codes work. Okay? We can actually run the same final model with different codes, look at the results, see how different those are or how similar those are, and that will give us a feel for the accuracy. If we're seeing completely different results, like on that one little dynamic problem we saw earlier, that would indicate that probably our answer is not very good. But if all those codes show the same numbers, then it means, okay, we don't have a mathematical problem with the idealization, so our only problem would be with the idealization or the loading we applied or the constraints. And that kind of gives us a little more confidence that the model might actually be good. When we increase the fineness, when we talk about the fineness of a model, what that means is, like, we could have a pen like this, and we could have a single element representing that and only give it axial compression, axial stiffness. Or we can use the same one element, and give it bending stiffness as well. Or we can divide it up into like 3 pieces, that's more fine. Or 100 little elements, that would be more fine. Or make a solid model with 5,000 elements in this. That would be a very fine model. That's what we mean by model fineness. Okay? We're often going to have to do some work. Just running the model isn't sufficient. Then we got to figure out what those stresses or whatever else loads mean that we get out of our model, and there's quite a bit of judgment involved there. And So we find that finite elements is a combination of engineering, of judgment, and of finesse. There's some art in that too. I'm going to try and help you. We're going to keep this stuff simple. We're going to learn to do the hand analysis. We're going to learn to do finite element models and to make quicker FEMAP kind of models. But I'm going to try and do that in a manner that helps you to start developing the kind of judgment you're going to need to become a good finite element modeler. Here are some commercial finite element programs that are available. MSc NASTRAN is probably one of the leaders. Here are some others that you may run into. So let's go ahead and let's take a look at what NASTRAN, how NASTRAN runs. Okay? Actually, I'm going to break it up right here. So this is the first half of our lecture. I'm going to break up the last part of our lecture as a separate lecture where we talk about NASTRAN models. That's all I got. Thanks.